Hi everyone, my name is Bailey Martin and I'm a PhD student from the Australian National University, working with Chris Lidman, Brad Tucker, Brian Schmidt and Dylan Brout. First of all, I'd like to thank the organisers of Cosmology from Home for giving me the opportunity to present my research, looking into the impact of host galaxies on Type Ia supernova distance measurements. Today I'll go through all the results of my recently submitted paper, in which we find that a correction for a host galaxy's oxygen 2 equivalent width may be more effective than the widely accepted mass step. So when we see a random bright object in the night sky, we have no idea if it's intrinsically bright or if it's just nearby. Type Ia supernovae solve this problem, as they've been observed to reach essentially the same absolute magnitude. This means that we can determine accurate distances because if they appear faint, they must be further away. Type Ia supernovae occur when a white dwarf star reaches the Chandrasekhar mass limit of 1.4 solar masses. Once the white dwarf surpasses this mass, the star is too heavy to be supported by electron degeneracy pressure, resulting in a runaway thermonuclear explosion. Now, Type Ia supernovae have been used for distance measurements for decades, and they've allowed us to constrain cosmological parameters that describe the structure and evolution of our universe. So we're able to determine these cosmological parameters by using a Hubble diagram, which shows a galaxy's distance modulus measured from its detected supernova against its redshift or recessional velocity. We can overplot a cosmological model with a set of values for the Hubble constant, the matter density of the universe, and so on, to see how well real observations fit a given model. So here I show the Hubble diagram given by the Foundation Supernova Survey, along with a flat lambda CDM cosmological model. Now, we can take the residual of the data relative to the model to see how well the model fits real observations. This Hubble residual is equivalent to the deviation in a supernova's observed magnitude from what we expect. So here I've plotted the Hubble residual for the Foundation dataset relative to my model from the last slide, where the brighter supernovae have negative values and the fainter supernovae have positive values. The scatter in supernova Hubble residuals is a significant problem, because it's too large to say with certainty which cosmological model is the most accurate. The goal of my research and of supernova cosmology in general is to reduce this scatter in Hubble residuals as much as possible, so that we can discern between different cosmological models of our universe. We can do this by comparing these Hubble residuals to different potential impacts on a supernova's brightness to look for systematic influences, which we can then correct for to improve the accuracy of our measurements. Now, there are many factors that influence a Type Ia supernova's observed brightness. This means that we need to apply corrections to the distance modulus to account for these systematic effects. Because of this, we call Type Ia supernovae standardizable candles. Here are some of the most common corrections that we apply to a supernova's distance modulus. So the stretch quantifies the shape of a supernova's light curve by describing the rate at which the supernova fades after it's reached its maximum brightness. This is an important correction to make because the stretch of a supernova is correlated with its intrinsic luminosity, with broader light curves being observed from supernovae with a larger peak brightness. We also correct for the color of the supernova with the parameter C. This is the B-V color of the supernova at its peak brightness, with positive values denoting redder supernovae and negative values denoting bluer supernovae. This color parameter accounts for both an intrinsic color luminosity relation for Type Ias, but also the impact of dust attenuation. Now, we have a term that accounts for selection biases in the sample, which is determined through simulations of supernova datasets. And then finally is this correction for the mass of the host galaxy. We apply this correction due to the existence of a mass step in the Hubble residual. So we find that after correcting supernova light curves, galaxies with a larger stellar mass produce supernovae which are slightly brighter than less massive galaxies. This figure shows the Hubble residual as a function of the stellar mass of the host galaxy, and we can see a clear increase in brightness as we move to higher masses. The physical driver of the host galaxy mass step is very poorly understood, but correcting for this phenomenon greatly reduces the scatter in the Hubble diagram, and so for the last decade, a mass correction has been applied to supernova light curves in almost every cosmology paper. Now, the goal of my research is to investigate supernova host galaxies more broadly, in an attempt to reduce the Hubble diagram scatter, while also really trying to understand the astrophysics and why supernova light curves vary depending on their host galaxy. Many studies have measured supernova host galaxy properties in an attempt to search for correlations with the Hubble residual. Correlations have been identified with the host galaxy's gas phase metallicity, stellar age, specific star formation rate, and of course the stellar mass. However, the significance of these results varies greatly from study to study. In most of these cases, broadband photometry is used to derive host galaxy properties, while a smaller number of studies use long-slit and multi-fiber spectroscopy. Now, integral field spectroscopy is arguably the most promising method of observing supernova host galaxies, as it allows a spectroscopic study of both the global properties of the galaxy as well as the local environment. In 2020, Rigaud et al. Used IFU spectroscopy to demonstrate a sharp step in the relationship between Hubble residual and the local specific star formation rate. In my research, I'm also obtaining IFU spectra at a higher resolution than the Rigaud study. In my recent paper, I analysed a sample of 75 supernova host galaxies from the Foundation Supernova Survey in order to search for correlations between host properties and the Hubble residual. I achieved this by using the WiFeS spectrograph on the ANU 2.3 meter telescope, located at Siding Spring Observatory in Australia. WiFeS is an IFU spectrograph covering a wavelength range of 3,500 to 9,000 angstroms, with a spectral resolution of 3,000, which allows me to measure a wide range of spectral features, which I can use to determine galactic properties. Now, currently I've only extracted global spectra from my observed data cubes, but I plan to analyse the local environments in the coming year. Once I have a galaxy spectrum, I need to fit a model spectrum to the data in order to obtain the galaxy's properties. To do this, I use the Python module ppxf, which stands for Penalized Pixel Fitting. ppxf combines single stellar populations from the Miles spectral library to produce a galaxy spectrum, which is then fit to the observed data. By optimizing the fit, ppxf produces a model spectrum of our galaxy, which can be broken down into stellar and gaseous components. In the top plot, I've shown an example fit to one of our host galaxies, showing the different components of the model spectrum. On the bottom is a plot showing the weight that each stellar population was given in the model spectrum, binned by age and metallicity. By looking at the gas spectrum and the different populations of stars that have gone into the fit, we can determine a number of important global properties, including the mass-to-light ratio, the average stellar age and metallicity, dust attenuation, and the equivalent widths of individual spectral features. So here I have my main results. Along the top, I have properties of the stellar component of the galaxy. So there's the mass-to-light ratio, the stellar age, and stellar metallicity. I'll note that while previous studies have found correlations with stellar age, we see no immediate evidence of a relationship, but that may change as our sample size increases. On the bottom, I have the properties derived from the gas emission lines. So on the left, there's the Balmer decrement, which is the ratio of H alpha to H beta. This is commonly used as an indicator of dust reddening, which has been suggested as the driver of the host galaxy mass step. Then I've also got the equivalent widths of H alpha and oxygen 2. I did measure the equivalent widths of 9 other emission lines, but these ones are the ones with the most relevant physical meaning, as they relate closely to the specific star formation rate. Now, more star-forming galaxies produce larger equivalent widths in the O2 emission feature. What we find is a 2.3 sigma correlation between the O2 equivalent width from the host galaxy and the Hubble residual. This correlation appears to be independent of supernova color. This O2 correlation is equally as strong as the host galaxy mass step in our observed sample, suggesting that it may also be a useful indicator of systematic influences on supernova distance measurements. The next property I looked at is the Balmer decrement, which is the ratio of H alpha to H beta flux in the host spectrum. The Balmer decrement has a base value of 2.86, which is set by quantum mechanics, and any value greater than this describes the amount of reddening due to dust. What we find is a 1.7 sigma linear fit to the complete sample, which is not quite enough to claim the existence of a correlation. But we do find something interesting when splitting the sample by supernova color. The blue supernovae show a 2.2 sigma correlation, while the red supernovae show a large scatter. This suggests that blue supernovae are not being accurately corrected for dust attenuation by the color parameter. There was a recent paper by one of my supervisors, Dylan Brout, and his colleague Dan Skolnick, in which they proposed a model of the intrinsic scatter in the Hubble diagram using a varying dust attenuation law that depends on host stellar mass. Using this, they were able to capture the observed trends between the Hubble residual and supernova color. We therefore expect that upon applying the host mass and bias corrections according to their model, our observed relationship should disappear. But this is not the case. So here I show the O2 relationship before and after correcting for the host galaxy mass and selection biases, according to Dylan and Dan's recent dust model. And we find that the correlation just doesn't disappear. We're still left with this 2 sigma correlation between Hubble residual and O2 equivalent width. Now, this is also the case for the Balmer decrement relationship, with the blue sample still showing a positive slope. This all suggests that the mass step correction isn't exactly doing a great job at accounting for systematics. But what if we use something else to correct supernova light curves? In our results, we found a correlation with the O2 equivalent width that was equally as strong as the mass step. So we decided to see what impact an O2 correction would have on Hubble residuals rather than a mass correction. What we found is that after correcting for stretch and color in the usual way, an O2 correction alone reduces the scatter in the Hubble diagram to a greater extent than the mass step correction. We also see a reduction in scatter when both an O2 and a mass correction are applied, but this doesn't show any clear improvement over a pure O2 correction. Now, we also looked at whether the O2 corrected Hubble residuals still show correlations with the other host galaxy properties. We find that the O2 correction alone removes the host galaxy mass step without applying a dedicated mass correction at all. This was not the case in reverse, which means that the mass correction did not account for the O2 correlation that we saw. This all suggests that O2 is more closely linked to this environmental systematic that's inducing scatter in the Hubble diagram. We also found that the O2 correction greatly reduces the significance of the correlation with the Balmer decrement that we see, which is not necessarily achieved by the mass correction alone. This is all a promising sign that the O2 correction may be more effective than the canonical mass correction that has been used extensively for the last decade. Now, what I really want to highlight about this is the actual practicality of an O2 correction. O2 is a bright spectral feature at 3,727 angstroms in the rest frame. This makes it measurable in optical and near-infrared spectra out to a redshift of around 1.5, which is beyond the upper redshift limits of most modern supernova samples. Since host spectra are taken in supernova surveys for the purpose of redshift measurement, this means that measuring the O2 equivalent width and implementing a correction is actually quite a feasible possibility. So that was an overview of my first lead authored paper, which was submitted to monthly notices in March this year. In this paper, I used a sample of 75 host galaxy spectra, but to date I've now obtained 202 host galaxy spectra in total. I still have 70 hours of observing time this semester, and I've submitted a proposal for 150 hours in the second half of this year, which, if successful, will give me a sample of around 400 host galaxies by the end of this year. Now, an obvious next step of mine is to repeat this analysis with the larger dataset, which will hopefully clear up a lot of issues about my current relationships lying at the 1.5 to 2 sigma level. There are, however, many other avenues that I plan on taking to investigate the impact of host galaxies on supernova distance measurements. Firstly, I want to get a better handle on the dust properties of these host galaxies. I've been working with Michelle Kluver and Tom Jarrett to obtain WiFeS infrared photometry for the hosts from the Foundation sample. I've now obtained the full dataset, and I've got some examples of some of this data in the top corner. I'm also interested in looking into obtaining radio data for these galaxies to obtain a dust-free measure of star formation. I'm also planning to measure the H1 gas mass in these host galaxies to see whether the mass step exists across the board or whether it only applies to the stellar component of the galaxy. Now, the WiFeS spectra that I've obtained are IFU spectra, but in my work I've only analysed the global properties of these galaxies. So another future plan of mine is to go back to these data cubes and measure spectral properties of the local environments, as this has been shown in the past to amplify the correlations seen in global spectra. So in summary, I've been obtaining IFU spectra of Type 1a supernova host galaxies to look for correlations between host properties and the supernova-derived Hubble residuals. In my recent paper, I find a correlation with the O2 equivalent width, a tracer of specific star formation rate, as well as a color-dependent correlation with the Balmer decrement, which traces dust attenuation. By investigating the impact of a dedicated O2 correction to supernova light curves, we find that it reduces the scatter in the Hubble diagram to a greater extent than the mass step, while also accounting for other correlations with host galaxy properties, something that the mass correction is unable to achieve. This all suggests that an O2 correction is more effective than the correction for host galaxy mass, which over the last decade has established itself as a core Type 1a standardization parameter along with stretch and color. With the observation of Type 1a host galaxies a necessary component of producing a Hubble diagram with upcoming supernova samples, an O2 correction is a realistic possibility, and it may help further constrain the cosmological parameters that describe our universe. Thank you.